This short talk is about pavement response to imposed subsurface deformations. The motivation is that typically pavements are exposed to surface loads, and the models that are available for engineering analysis are dealing with these surface loads, but in many situations we have subsurface sources that dominate the performance. For example, if you have the pavement founded on active clays or collapsible soils, or if you have subsoil erosion or some void formation, and of course underground utilities, tree roots, and freeze and thaw action. Here are some pictures of these situations where you can see that the pavement is deformed due to sources originating at the subsurface. So a new model is offered. Here you have a cross-sectional view of the model, and this is an axisymmetric case for now, where we have the surface and we have a subsurface, and the difference between them is the pavement structure and all inert subgrade layers. And in this example, I have expansive material or expansive soil below the subsurface line. So as the expansive soil starts to expand, pushing the pavement from the bottom, you can see here that the surface is also deformed. And at some point, we have an axisymmetric deformation imposed at the surface, at the bottom of the pavement, and we have an axisymmetric deformation generated at the surface. There's a difference here between the peak deformation that is imposed and the peak deformation that occurs at the surface. There's also a difference between the width of the axisymmetric bulge here. A with subscript H is denoting the width of the shape here, and the surface has a different width. Normally, the peak deformation is attenuated at the surface, and also the deformation width is wider or larger at the surface. If we look at this from a mathematical viewpoint, then we have the pavement exposed to an underground deformation of the form that is of a Gaussian form. The formulation you see here is for an elastic half space. It's an axisymmetric formulation. Here is the imposed bulge at the subsurface, where the peak displacement is QH and the width of the Gaussian shape is AH, and the interface is assumed smooth, and the model computed surface vertical displacements is given by this expression, where you have A, B, C, and D are functions of M. It's an integration parameter, and also QH and AH. This is just an example. The modeling is allowing calculation of all responses in the system, and also to consider layered situations. The full derivation and some other examples are given here in this article that was published in Computers and Geotechnics. The title is Analysis of Pavement Response to Subsurface Deformations. Some concluding remarks here. So we have a new analytic model for pavements that are exposed to underground movements. The model supports the computation of stresses, strains, and displacements everywhere in the system. The imposed deformation field is a Gaussian function, but the Gaussians can serve as radial basis functions and provide a multi-scale representation of any shape of interest. The potential utility of this theory is that it can serve as a tool or as a kernel for mechanistic modeling of pavement roughness. Thank you for your attention.